Oh, okay. We go back. Where's the front?
Go back.
This is next.
Go back.
Okay, gracias. Hola, everybody. Gracias. So today I'm going to talk about solar energy integration and challenges in rooftop sector. So basically, I'll focus on some of the issues that we have been doing research in our university, which is Concordia University in Montreal, Canada. And also, I'll discuss about a project I'm doing with India under the collaborative Canada-India collaborative project scheme. My collaborators in Canada are listed here, Professor Athenaitis and Lee. And from India, it's Professor Reddy and Rao from IIT Madras. Okay. So as you can see that there is tremendous growth in solar energy and alternative energy implementation around the world. Obviously, China is well ahead in the game, but other countries are catching up, including India. We see two kinds of applications, or application of the same thing, but in two kinds of climatic condition. One is a very, very cold country like Canada, and very, very hot country like India. Now, you might ask a question, is that if you look at a country like India, there is a greater solar potential, greater incident of solar radiation, and country like Canada, where the duration of solar exposure is lower, so potential should be lower, right? But you will be surprised to know that Canada also has tremendous potential in solar energy harvesting, because lower temperature also allows you to gain higher efficiency in terms of the solar power generation. So, but the design of the application has to be a little different. In Canada, because it's a cold country, we have a higher demand of home energy usage or heating load in the buildings. So most of the winter season, we have to keep our indoor air heated to a comfortable temperature. While in the warmer climate, we have to keep the temperature cooler. Now, one can argue that heating is easier than cooling, okay? So that way, harvesting heat energy from the sun, no matter how small it is, can be very useful. So if you look at this, these are three examples of PV system usage in buildings. One is right in my city, in Montreal, where a public library has been installed with PV system. But this is an experimental project where our university was heavily involved, where they have installed the PV system in three different configurations. One part is to generate just electricity. Other part is to generate electricity along with harvesting the thermal energy. And the other part is that PV system with thermal, but that part of the thermal energy is not utilized. And basically, we wanted to compare the efficiency or efficiency gain of one system over the other. The middle system, which is, we call it Solar Decathlon, which is a student project. So about 25 undergraduate and graduate students participated in this project. So they basically built this building with solar energy integration, and they disassembled the building, transported to China for a competition, and assembled it there. So they raised about $500,000 to build that building and their transportation cost and all these things. And the competition went very well for them. They have won in many categories, and overall they came in second or third among all other competitors from Europe, North America. Even there were a couple of teams from India. So one thing they learned from this project is that the way we have integrated the solar energy or the PV system in this library, which is designed for cold climate, this decathlon was designed almost the same way, but when they built it in China, the temperature, the climatic condition was not really matching. So they faced a lot of challenges, okay? And for Indian condition, obviously those challenges will magnify, so therefore the design has to be a little different. So how so? In the first system, we integrate the solar panels flushed with the building components, which could be roof or the facade, which is wall. And we normally leave an air gap between them, and that air gets heated up much higher than the ambient temperature. And that heat needs to be drained out somehow or used. So normally there is a fan or ventilation system to take the heat out of that, or we can reuse that heated air for heating the building, because we need heating in the winter time, or we can use it through a heat exchanger to warm up some part of the waste ventilated or exhaust air. But while in high temperature regime, this temperature becomes too high to recover that heat or use that in any way, unless you really capture that heat and use for heating water or something, okay? And also the amount of the air gap cannot be narrow. Air gap has to be really big. So it is better if to keep that air gap fully ventilated. That way this overheating problem would not arise. So this is one design concept. The other design concept is if we trap that heat and use it somehow, one could be the heating water. The other is, we'll talk about desiccant cooling system. Like if you look at, there could be two kinds of situation in hot climate. One is hot and humid. Another could be hot and dry. So in hot and dry condition, we can use evaporative cooling, where we basically throw in moisture which absorbs heat. While in desiccant cooling system, we use this heat to dry up the desiccants, okay, and use that desiccant in the indoor environment to draw up air from the water from the air. So when we draw up water from the air, it heats up the air a little bit, but cooling that air becomes much more easier. So the load on the air conditioner becomes low. So that way we gain. So this is called heat-driven cooling. So we are using heat to basically cool the building. So this is a picture from our lab. We have the state-of-the-art lab for solar energy experiments, where basically there are high-powered lamp which can generate the light and heat in the perfect mixture to simulate different conditions of sun. And then we can test different PV system under that environment. And our center is called Center for Zero Energy Building Studies. The idea is that in, say, we are looking at a building at a colder climate where it needs a lot of energy to heat the building and run all the utilities. So the building, which is installed with enough renewable energy components, that generates enough energy so that we don't need any energy from the grid. So that would be a perfect example of zero energy houses. There were some experimental houses built in Canada, which are zero or almost zero energy houses. In the Indian context, probably we can go in a little bit better. We can do a little bit better. Indian or Peruvian context or any hot climatic condition is that the energy demand of a building may not be very, very high. So PV system can generate excess energy, which can also be utilized for something else. So this is again the same building, the Varin Library building, which generates about 110 kilowatt of energy with BIPV system. We call it BIPV, this Building Integrated Photovoltaic System. We also add a T at the end when we capture the thermal energy as well. So we call it BIPV-T system. So I'll not go into details of this picture. It's basically, schematically, it shows that how the airflow occurs in different components. We have two parts in the PV system on the roof. One part just exhausts the hot air, basically waste the hot air. The other part utilizes the hot air which goes through an air handling system, and heat recovery fan captures some of the energy. This is some of the experimentation or measurements done on the building to see what is the cavity air temperature, what is the ambient temperature, and what kind of solar heat it produces. And based on these measurements, it was figured out that the electrical efficiency is around 15%, 15.5 or so. That's the normal efficiency in this kind of condition, while the thermal efficiency could be quite a lot. So combined efficiency can be calculated as a high number. So which basically indicates that it is good to capture not only electrical energy from the PV system, it is important to capture the heat energy as well. So then the system efficiency increases to a great deal. So this is some of the simulation results to basically to see if we can model this system in a computer software, generate the same kind of results. Why do you want to do that? We want to use that information or that experience to simulate the conditions in other buildings so that we can design them better. So this is the continuation of that. So in this context, I want to present this project, which is funded jointly by Canadian government and Indian government, which is called IC Impacts Projects. IC Impacts is a research network which works with Indian government and Canadian government. In Indian government, the partner was Department of Science and Technology, and our collaborators were from IIT Madras. So what we have been doing here is that we are looking at design issues of buildings with photovoltaic systems in Chennai area. Now, Chennai is a very hot area, so basically we were looking at a situation where this desiccant cooling can be utilized. So this is one of the example buildings where it's a medium-rise apartment building. Typically, this kind of buildings has lower floor as commercial floor. And in Indian situation, we normally don't have central air conditioning in this kind of buildings. Usually they are localized air conditioning system. While the commercial component could have significant usage of the air conditioning system, but mostly utilized in the daytime. So that's why it makes sense we utilize the solar energy fully in order to cool the area. This is, we drew the inspiration from the building that we designed at Concordia, which has a part as a building integrated system on the wall. This is the system diagram. I'll skip. Looks like I don't have much time. So desiccant cooling system works the way as we discussed. So at IIT Madras campus, we are building a test house, which is 1 bedroom, very tiny house, but basically it will be integrated with the photovoltaic system, with the heat-driven air conditioning system, and other sustainability features, and we'll take measurements and use it as a test bed to design other systems. Okay, I'll skip this. So basically, this is the description of the project. I can skip this. So basically, I want to summarize in a way that solar energy integration to building components such as rooftop and building facade has a tremendous growth potential. The technology works differently in cold climate and hot climate, but one can learn from the other. That is the whole purpose of this IC Impacts project. And in hot and humid climate, heat-driven cooling such as desiccant system can be very beneficial and increase the system efficiency. Integration of PV system on the roof and facade provides an important opportunity. And while electrical efficiency of the PV system is good in cold climate, it's not so good in hot climate. On the other hand, thermal efficiency of PV system is not so good in cold climate, but very good in hot climate. So when we combine them, we get the best out of it. So with this, I want to stop, and thank you very much. Gracias. If you have any questions.